A Kubernetes cluster is a highly dynamic environment, constantly spinning up and shutting down thousands of individual containers across multiple machines to meet demand. If you look at standard Kubernetes documentation, you'll see three primary ways to expose containers to network traffic: a ClusterIP, a NodePort, or a load balancer. This presentation often leads engineers to treat these three options as a multiple-choice question, assuming they represent completely separate parallel routing pathways into the cluster. But that mental model is entirely backwards. Kubernetes networking is strictly additive. These services stack on top of each other. Load balancers wrap NodePorts, and NodePorts wrap ClusterIPs. If requests fail to reach a pod, you can't troubleshoot the network until you understand exactly how this dependency chain operates at the node level. We start at the foundation, the pod. When the scheduler places a pod onto a worker node, it gets a specific IP address. But pods are ephemeral. If a container crashes, that pod is destroyed. When a new one replaces it, it gets a completely new IP address. Reliable internal communication becomes impossible if destination addresses vanish without warning. To fix this, Kubernetes introduces the ClusterIP, a stable, virtual IP address that doesn't belong to any physical network interface on the machine. Instead, it relies on a node-level daemon called kubeproxy. Kubeproxy continuously updates the local operating system's IP tables to map that static cluster IP to the transient pod IPs, using an up-to-date list called endpoint slices. This mechanism functions as an internal Layer 4 load balancer. It operates on raw IP addresses, blindly forwarding packets based on these translation roles. The ClusterIP provides the baseline stability the system needs, ensuring internal services can talk regardless of how quickly pods churn. That covers internal traffic, but a ClusterIP is strictly restricted to the flat internal network of the cluster. If a client on the public internet tries to hit that ClusterIP, the request drops at the perimeter. The internal address is unreachable from the outside. To bridge this gap, we use the next component, a NodePort. A NodePort opens a specific port on every worker node. Traffic hitting this port never bypasses internal routing. It is immediately handed to the exact same IP table rules established by the ClusterIP. The NodePort acts as an external wrapper, extending the reach of the ClusterIP out to the host machine's network interface. By forcing all external traffic through this NodePort to ClusterIP handoff, Kubernetes ensures that its internal load balancing logic and endpoint tracking stay consistent. Exposing raw worker node IPs to the public internet presents significant security risks and makes scaling traffic across a growing cluster difficult to manage. This requires a dedicated gateway, the load balancer. When you create a load balancer service, Kubernetes delegates the task to your cloud provider or a tool like MetalLB to provision an external device with its own public-facing IP address. So, where exactly does this load balancer send the requests it receives? It distributes the incoming traffic across the open node ports of the underlying worker nodes. The load balancer hands the packet to the NodePort. The NodePort feeds it into the ClusterIP rules, and the ClusterIP forwards it to the active pod IP. This entire nested chain operates at OSI Layer 4. It does not look at the content of the data. It simply reads source and destination IP addresses to move packets at high speed. The load balancer secures the cluster's perimeter while utilizing the routing engine already distributed across the nodes. Modern microservice architectures require more granular control. A user visiting a website might need to be routed to different backend applications based on URL paths, like hitting a payment service versus a shipment service. This illustrates the limitation of Layer 4 routing. To isolate services by path using only load balancers, you would have to provision and pay for a distinct external IP address for every single microservice in the cluster. To prevent this infrastructure bloat, Kubernetes utilizes the application layer, Layer 7, using an ingress controller. An ingress controller is a specialized proxy pod, like Nginx, running inside the cluster. Because it operates at Layer 7, the ingress proxy can look inside the HTTP request to read the specific URL path the user requested. It acts as an API gateway, comparing that URL path against a set of routing rules you define. When the ingress pod identifies a request for the payment directory, it forwards that traffic directly to the dedicated ClusterIP for the payment microservice. We can now trace the complete journey of the web request. It starts outside the system, when a DNS server maps your domain name to your load balancer's public IP. That load balancer takes the layer 4 traffic and passes it to a worker node via its open NodePort. The NodePort hands the traffic to the internal IP tables, routing it to the ClusterIP of the ingress controller. Inside the cluster, the ingress pod reads the application data, identifies the URL path, and forwards the request to the target microservice's ClusterIP, which finally lands the packet inside the container. This networking architecture is a unified stack of nested abstractions, each layer building upon the last to create a stable pathway through a distributed system.